Yeah, I'm glad my reputation precedes me. Thanks for the opportunity to speak here. I chose the title Adventures in Galaxy Gas Physics, which basically means I'm going to be talking about a couple of different topics. But from a physics standpoint, galaxies are wonderful because so much physics matters for them. We think they grow out of quantum fluctuations seeded in the Big Bang. They grow due to general relativity and gravity. As I'll describe in the Colloquium, the mass scale for galaxies is set by atomic physics. And then their subsequent evolution is determined by fluid dynamics and star formation and black hole growth, a lot of which is tied to nuclear physics. And so no matter what you study as a physicist, there's a fair chance that it actually really matters for galaxy evolution. Galaxies are kind of a wonderful sort of playground to see how all of the physics in the universe works together and combines to make these objects, one of which is our home. So I study fluid dynamics, and a theme of my research is that new discoveries in fluid dynamics, new processes that we find, can have unexpected and sometimes surprisingly large impacts on galaxy evolution. And I'll describe three such topics today. The first one's going to be about thermal instability and the production of cold gas in galaxies, and I'll describe why that's so interesting. The second topic is going to be about convection and mixing, mostly in galaxy clusters, and how plasma physics influences that. And then the third topic will be about entrainment and fragmentation of cold gas in galaxies. Still an unsolved problem, but I'll describe ongoing research into a number of puzzling observations. But starting off with thermal instability in galaxies, this is actually really motivated by observations like this one of galaxy clusters. And I think this group knows that despite the name, a galaxy cluster you should really think as one monolithic object. It's like a really, really big galaxy. In this case, about 1,000 times the mass of the Milky Way. And these objects are so massive, their gravity is so strong, that the gas in them is at 100 million degrees, and we see it glowing in X-ray emission. That's not the weird thing here. The weird thing in this particular cluster is shown in the right. This is an optical image of the same frame that we see in the X-ray. And typically in astrophysics, right, we think optical emission traces starlight. And indeed, what you see here are all the stars in all the galaxies that are members of this cluster. But in the center, you see some pink fuzz. And in this image, pink corresponds to H-alpha emission. And so this pink emission is coming from neutral hydrogen in the center of the cluster at 10 to the 4 degrees or less. And it's right in the middle of this ball of gas at 10 to the 8 degrees. And so we have spatially co-located two different phases of gas. They differ in temperature by a factor of 10,000. And so that's not what you expect. A natural question is to ask what's making this cold gas in galaxy clusters. And I think I'll answer that. And the answer is going to turn out to be so mundane that this isn't the right question to ask. The right question is actually, why doesn't it always form? It's so easy to make cold gas that the scientifically interesting question is instead that we don't see it everywhere. And so I'll show a better observation just to kind of lay out the important physical properties. This is a Hubble telescope image of the same field, higher resolution. And even at Hubble's resolution, these filaments of cold gas are unresolved. And that's the strange part. So if you're inside one of these filaments, the gas is 10 to the 4 degrees. And if you take just a tiny step in any direction, immediately the gas jumps up to 10 to the 8 degrees. And so we have an incredibly sharp temperature gradient. And there are a lot of processes in astrophysics that hate temperature gradients. But if you have thermal conduction, or if you have turbulence, or really if you just have gas motions of any kind, it's easy to imagine smearing out temperature gradients, smoothing them out with time. And so when you see a gradient that's this sharp, in spite of dissipative processes, in spite of diffusion, it's an indication that there's some physical process that's amplifying temperature gradients, making clouds of cold gas like we see here. In this case, that's almost certainly thermal instability. And so just to be clear what I mean by thermal instability, I'm imagining gas in some equilibrium where cooling is balancing heating. And if I define the net cooling rate, that's cooling minus heating, okay, in an equilibrium, that's going to be 0. And the critical part is the derivative of that cooling rate with respect to temperature, the appropriate thermodynamic derivative as gas cools. If that's negative, that means if I start in a thermal equilibrium, if I cool a little patch of it, it responds by getting a net cooling rate, and it'll cool further. This runs away to low temperature. This amplifies temperature gradients and can explain observations like this. And moreover, if you put in the sort of cooling and heating physics that we think is relevant in clusters, you find that it is thermally unstable in this way. And so I think that is the origin of this gas. It's a little bit boring, but that doesn't mean that we're without surprises.
This is evaluated at T of 10 to the 8. That's what you mean. It's thermally unstable at 10 to the 8 degrees such that it will cool.
You're thermally unstable actually over a wide range of temperatures. The key is that it's a derivative at constant pressure, so it's isobaric cooling. So that's kind of a mundane explanation, but there is a surprise in here. And you can see that when you run a nonlinear fluid dynamics simulation. And so I've done a simulation, in this case, of gas with gravity and cooling, the physics that's relevant for galaxy clusters. And I've arranged it for the gas to be thermally unstable. Okay, this is realistic, but it also means I've put in an exponentially growing instability by hand. And so what the simulation does is not a surprise. I put in an exponentially growing instability. It grows exponentially. It amplifies temperature fluctuations and makes cold clouds of gas. That's exactly what we see, right? So this is similar to what we see in clusters, but I'm not allowed to declare victory because I put in the answer by hand. The surprising thing is actually in this simulation. It's precisely the same physics, precisely the same code, all of that. This also has an exponentially growing instability. And I can go into the code and measure how fluctuations evolve with time and confirm that they exponentially grow. But they don't do anything. They saturate at a low amplitude. They drive waves, but they do not produce clouds of cold gas. And the difference is that I've changed the ratio of the cooling time to the freefall time in this atmosphere. And so even though I've assumed thermal instability, I've put it in by hand, that doesn't necessarily imply that I can make clouds of cold gas. There's another parameter in the problem, the cooling time over the freefall time, that determines the nonlinear saturation of this instability. And empirically, from running simulations, we only see cold gas when the ratio of these two times falls below some threshold. Numerically, it's about 10.
Sorry, is the linear growth rate the same in both the left and right simulations?
It's either the same or it changes by a factor of 2. Okay. I don't remember.
Okay.
But they've both
run. It's not a ratio of 100 here. Right?
They've both run for 20 linear growth times.
Okay.
So I've scaled the simulation to that. Okay. So if it were linear and self-similar, they would be the same. But there's a nonlinear effect.
And can you just say again in the right-hand picture what happens? It just sends pressure waves through?
They're internal gravity waves.
Gravity waves.
And I will, that perfectly anticipates my next slide. So if you look at what happens here, we know that gas in hydrostatic equilibrium is stable. And in physics, if something's stable, it means that it oscillates. If you pluck it, there's a restoring force that brings it back to its equilibrium, and without dissipation, that drives oscillations. And the stable oscillation associated with hydrostatic equilibrium is the internal gravity wave. And so we see that all the time in hydrostatic objects. What cooling does, what thermal instability does in particular, is it drives internal gravity waves to be overstable. It destabilizes that wave. And so for the sort of astrophysically relevant regime, we get things that oscillate at the Brent-Weissala frequency, the period for those waves, and then it grows exponentially on the cooling time scale. And if I go back to the simulations and I measure wave amplitudes as a function of time, this is exactly what we see. There's exponential growth at almost exactly the cooling time. So they grow almost perfectly exponentially, the way that you'd calculate in thermal instability. And then getting back to Omer's question, in the linear theory, you can have a switch. Basically, you take different roots of the equation, and it changes by a factor of 2, and it starts to oscillate. And you see that here, but the point is that it's still exponential. And the exponential growth is going to win over everything.
So the red curve is just the other root?
This is a simulation with a longer cooling time.
But these have all run for
equal numbers of growth times.
Right. Okay.
We're just having an overstability, basically. Is that from what I understand on the math?
It switches from a purely exponential mode to an overstable mode. Yeah. But the key isn't the linear physics. And I think this is actually what set this field back for a long time, was a focus on the linear physics, which turns out not to be the interesting part. The key is that these are all growing exponentially, but some grow longer than others. And so if I run a simulation with a different value of T cool over T free fall, if the cooling time is short compared to the free fall time, it grows exponentially for longer, it reaches higher amplitude, and then it stops. If I run a simulation with a long cooling time compared to the free fall time, it still grows exponentially, but it doesn't grow for as long. It stops at a lower amplitude. And the astrophysically important thing is where it stops, and that's a nonlinear effect. And so if we want to understand the astrophysical implications of this, it's the steady state part of this that's important. It's not the exponential growth.
So Mike, at 10 to the 8 Kelvin, I mean, if you didn't put up a cooling curve, so how are you getting a thermal instability at 10 to the 8 Kelvin?
Bremsstrahlung cooling?
So the Bremsstrahlung is doing it?
Yeah.
And you're balanced with what's your heating?
I'm assuming, this plot was made assuming heating that's constant per unit volume. So
Some cosmic ray thing.
Yeah.
Feedback or something.
You can do the same thing with heating per unit mass. Suching also independently discovered this when he was reproducing this result. You scale the cooling time appropriately, and the linear physics exactly goes away.
Sure.
So this is something that's very calculable. But the reason Bremsstrahlung is thermally unstable is that these are isobaric perturbations. So the density squared wins out. If that was your question.
So when you go to the overstable limit, right, which is still unstable, so if you did a quasi-adiabatic calculation of an internal gravity wave, and you put this physics in, if you did a quasi-adiabatic calculation, you'd find the overstability. And that's, I guess, that's your red.
Yeah.
That's the red limit.
It still grows exponentially.
Right.
And the point is that, at least in the centers of clusters, the cooling time is shorter, much shorter than the edge of the system. And so if it grows exponentially, it's going to grow. And the thing that matters isn't the growth rate, it's where it stops. And so we need a theory for where it stops.
But once then, maybe just to connect to the observational picture more, once you saturate at, say, 1, then what gives you the rest of the... Then you're just assuming that you have compression and you approach pressure equilibrium, or?
Oh, yeah.
How do you get to the actual density contrasts?
Once delta rho over rho is of order unity, if I have large density fluctuations, then if I take gas and I compress it by a factor of 2 or something, the cooling rate goes like density squared. This is a situation where feedback isn't really going to work. If delta rho over rho gets big enough, it's just going to collapse and make a cloud.
Okay, so you just feel like you need to get to a few and then you're done.
Yeah.
And then you'll form. Yeah.
Okay. And you don't really see that in this plot because it's a volume-weighted RMS average over the domain. So this is really sensitive to the amplitude of the waves and not so much once they become nonlinear. But we need a theory for this part. That's the critical part, and it's nonlinear. It's not going to come out of the linear physics. And so since it's a steady state, we want to look for a balance between dissipation and driving of the waves. We know the waves are being driven by cooling, and so we need to match a dissipation rate to that in order to get a steady state, which we see from the simulations. And we can just make the ansatz that the dissipation comes from turbulence. And so if the waves are driving velocities, if those drive turbulence that act as a dissipative effect, the dissipation rate at a given scale k goes like k times the velocity on that scale. The velocity is not typically what's observable in X-ray observations. I want to relate it to the density, and I can use the structure of the internal gravity wave to do that. The velocity and density fluctuations are correlated by the properties of the wave. And then if I look for a steady state, I know I'm driving them on the cooling time. They're dissipating due to turbulence in this way. A couple lines of algebra, you arrive at an equation for the steady state amplitude of the fluctuations. Okay, and it goes like a power law in this parameter t cool over t free fall that I said was important. And if you keep all of the terms, you get a ratio, the free fall time divided by the internal gravity wave period, that's of order 1 in hydrostatic systems. And then interestingly, you get this term, lambda over h. You get the largest fluctuations on the largest scales. And that's simply because the dissipation is the lowest on the largest scales. And this is good because observationally, the distributions of cold gas typically occur in large scales.
So is this strong turbulence assumption valid in the case where you've got a small saturation amplitude, or this is just determining the critical density amplitude at which you're below which it doesn't matter? I mean,
That's a good question. I think this is. This theory is really interesting when you have large amplitude things,
Yeah.
right? It's a theory for why you don't make cold gas.
Right.
If the cooling time is really, really, really long,
Right, then.
it's less surprising that you don't make cold gas.
Okay.
So there's kind of
The point is it works where you need it to work. That's
Yeah.
really, yeah. Okay.
And also, this breaks down once it becomes nonlinear and you form these clouds of cold gas, right? But then that's the case where the cooling time is very short. It's not surprising what happens. I think this is interesting because there are a range of galaxy clusters where the cooling time is short and you would expect cold gas, but you don't see it. If that makes sense. So anyways, you get this power law for the amplitude in terms of T cool over T free fall. And that agrees almost exactly with what we see in simulations. Should really focus on the blue curves. And going back to Lars's question, one of these is heating per unit mass and one of them is heating per unit volume. And if you scale it appropriately, it's beautiful. It completely goes away. I don't actually remember which curve is which. And then this is for different ratios where I tried to control T free fall over T buoyancy to test that. It turned out I didn't have total control over that parameter because the atmosphere evolved. So this is a nonlinear theory that actually explains very nicely what happens in nonlinear simulations, which is great. This doesn't happen a lot in fluid dynamics. But to impress astronomers, you usually can't just explain a simulation. You have to explain data. And so this is my attempt at that. Professional observers have since done better, but I'm showing the plot that I made. This is a handful of galaxy clusters for which we have exceptionally good X-ray data. And I was able to measure the ratio T cool over T free fall as a function of radius in these clusters. And I've colored the curves red if the clusters are known not to have cold gas, and blue if the clusters are known to have cold gas. And T cool over T free fall has this characteristic shape, kind of a U shape. The density falls at large radii in clusters, and so the cooling time becomes long. And then clusters have things called cores, where the central density of the cluster is depleted, we think due to AGN feedback. And so similarly, this rises. The cooling time stays roughly constant, but the free fall time gets shorter and shorter towards the center of the cluster. And so the minimum is at the edge of the core in the cluster, kind of the region where the AGN's influence is extending out to. And indeed, the minimum occurs at tens of kiloparsecs, which is actually exactly where these filaments are observed in clusters. So the theory nicely predicts where cold gas forms. And then also, the clusters that have cold gas are exactly the ones where these curves dip below the threshold of 10. So amazingly, the magic number is 10. That's something that's calibrated in simulations. We see it also in simulations, or in observations. And the clusters which don't have cold gas are ones where these curves are systematically higher.
Sorry, so that magic number of 10, I think you admitted to me yesterday you don't understand where it comes from, but it does come out of simulations.
It does.
Okay, interesting. Okay.
Minor dependence on the simulation setup.
Yeah, okay.
But it's of order 10. It might be 20.
Okay.
But it's definitely greater than 1.
Yeah.
And we don't know why.
Well, let's slow down. But I mean, your hypothesis is you're taking a state that's in hydrostatic balance as your perturbation state. So
Yes.
you want this inequality to be bigger than 1. So you even have something to think about in terms of perturbation problem.
That's right, yeah.
If it was 1, you wouldn't have a state you could even start with.
Why 1 is also exponentially unstable?
This is the cooling time relative to the hydrostatic crossing time.
Lars is saying that taking an equilibrium state with all the time derivatives equal to 0 does not make sense if the cooling time is of order the dynamical time, which I agree with. Yeah. So it's nice that it's greater than 1.
Presumably why you have some kind of a near hydrostatic. I mean, it has to be bigger than this to have something that emits in
Yeah.
anything like a hydrostatic state, right? The cooling time has to be longer than that.
Yeah, so the nonlinear physics picks out 10, and this picture would not have worked if it were 1 or less than 1. So we got lucky, I guess. Anyways, so this is a theory. It explains the results of simulations modulo this parameter that I have to put in that I can measure. It explains where cold gas forms in clusters, and it nicely predicts which clusters have cold gas and which ones don't. It has even farther reaching implications than that.
Can we go back for a minute? So let's talk about a case that's the dashed red line way up high.
Okay.
Where the cooling time is long. Right?
Yes.
So for that one, would you just argue that the reason you're not seeing H alpha is you haven't had adequate time? Because you'd still say it's unstable.
Okay, so this one.
Enough clock time?
So this plot compares T-cool over T-freefall versus just the cooling time.
Okay.
And it's meant to show that T-cool over T-freefall better separates these points than the cooling time. Again, observers have since added more points to that. So that is probably this one. The cooling time is still a gigayear. So it's less than the age of the system.
Right.
So in all of these cases, there has been enough clock time for cooling to happen. The key is that it just doesn't happen by making multi-phase gas. And when you do cosmological global simulations, you need feedback. You need some sort of heating to offset that.
And so somehow feedback just happens to set these profiles up, and then you're saying in some cases you would see cool gas, and in some cases you would not.
Precisely where I'm going. So this theory for when you make cold gas and when you don't, which is what I just described, not when cooling happens, but when it's multi-phase and when it's not, that has far-reaching implications because cold gas is very important for the structure of galaxy clusters. And that's what this simulation is meant to show. It's something that Pratik Sharma and I ran. And the big simulation groups have since done more sophisticated things. The idea hasn't changed all that much. This is a simulation of a galaxy cluster, including cooling and a very simplistic model for AGN feedback and gravity. And it has this physics of thermal instability in it. Naturally comes out of it. And I'm showing snapshots of the simulation at different times, and then the accretion rate, which is separated into the accretion of hot gas, shown in red, and accretion of cold gas, shown in blue. And the point is that the initial condition, T-cool over T-freefall, is greater than 10 almost everywhere. We actually didn't, it's close to 10. We didn't cook it to be that. This was actually fit to data from a galaxy cluster, and it turns out they cluster around 10. And there's no cold gas in the initial condition. The black hole accretes at the Bondi accretion rate, which in clusters is typically about a solar mass per year, which is reproduced in the simulation. And a solar mass per year does not provide enough feedback energy to offset cooling in the atmosphere. And so it cools, but it cools in a single phase, not multi-phase. And so it cools, gas flows in, the density rises.
Are you assuming for the efficiency of converting cooling gas into feedback energy, or are you just using some standard number for radio mode or quasar mode, or what is the? It's 5 times 10 to the minus 3, or?
Yeah, of order that. It's a very simplistic model. And we assume that any gas that reaches the inner boundary condition accretes onto the black hole, which is, of course, a complex process. The point that I'm going to make is that this is very insensitive to the physics of that feedback. So initially, you can't offset cooling, but the atmosphere cools in a single phase because T-cool over T-freefall is greater than 10, flows in, density rises, T-cool over T-freefall drops. When it crosses this threshold, all of a sudden you start making multi-phase gas, and it's like turning on a switch. And once you form cold gas, they free fall, they plummet through the atmosphere. And the accretion rate now, it's not just in the hot phase, you're accreting cold gas, and it jumps up by a couple orders of magnitude. And so 1 solar mass per year was not enough to offset cooling. 1,000 solar masses is too much. And so all of a sudden, you're way overheating the atmosphere. You're puffing it up, expanding it, gas moves out, the density falls, until you again cross this threshold, and you're not making cold gas anymore. And so semi-independent of how the physics of cooling and feedback work, the point is that it's like a binary switch. You either have cold gas or you don't, and your accretion rate jumps by orders of magnitude based on that. And so other groups have done more sophisticated simulations with more realistic models of AGN, with biconical winds and all sorts of different assumptions. But basically, because this is a binary switch, you're always going to get the same answer. So the direction that we took it wasn't to do more sophisticated simulations, but actually to make an ansatz that heating and cooling self-regulate to be near this marginal threshold for nonlinear stability. That however feedback works, it's probably going to do something like this. And this is something you can use actually to make analytic models for the structure of galaxy clusters. And so the question we wanted to answer was what determines the density of the gas in the centers of clusters. And it's motivated by a long history of X-ray observations. So there are self-similar scaling relations for galaxy clusters that were worked out in the 80s, essentially assuming that gas behaves like dark matter, which we know that it doesn't. But if you do that, you can work out a relationship between the X-ray temperature and the luminosity of clusters, and the luminosity should go like temperature squared. And it doesn't. The relationship is steeper than that, which means gas doesn't behave like dark matter, which is not a surprise. And the sign is that you have to lower the density of gas in clusters. Also not a surprise. Some of the gas turns into stars, some of it gets blown out. And the discrepancy gets worse as you go down in mass. Again, not a big surprise because the cooling time gets shorter. But the point is that this is data that we can now try to model. And we can explain it quantitatively just with this ansatz. We don't need a cosmological simulation. And so the way that it works is if you take a self-similar model for a galaxy cluster, you calculate what T cool over T free fall as a function of radius looks like. It's roughly a power law, which is typically what you get in all these self-similar models. And as power laws do, it goes to 0 at small radii. But I'm saying that based on the physics of thermal instability, it's not allowed to get below 10. Okay? This gas cannot be in the hot phase. And I'm not saying anything about what happens. It could turn into stars, it could get blown out, it could get pushed out to slightly larger radii. All I'm saying is that this gas cannot be in the hot phase in the center of the cluster.
And that results in catastrophic cooling, AGN feedback, and repuffing.
Exactly, yeah. And so exactly what happens, right, you could do a simulation, and the details will depend on the details of the simulation. But if you focus on the hot gas, the X-ray observables, this has to be what happens. And then a typical thing that happens in hydrostatic atmospheres, if you dump a lot of energy into them, is that you get a constant entropy core. Basically comes from the physics of convection. And what a constant entropy looks like in a curve like this, T cool over T free fall dips up. It's actually kind of what we saw in the data, if you remember. And then physically, what I'm doing to raise the entropy in the core or change T cool over T free fall, however you think about it, is I'm lowering the density. So again, this is gas that just cannot be in the center of the cluster. It's either pushed out or turns into stars, but something happens to it. And I can calculate this density profile. And for different masses, the sign is that as you go down in mass, the cooling time becomes shorter. The gas is cooler, cooling's more important. So cooling's a bigger problem. I have to get rid of more and more gas as I go down in mass. That means I'm carving out a bigger core with lower density. And so as I go from a massive cluster to a group to a massive galaxy to, admittedly, an extrapolation to something like a Milky Way gas mass galaxy, you can calculate density profiles as a function of radius. You can integrate over that to get X-ray luminosities and X-ray emission-weighted temperatures to make curves which then compare to these data points. Depending on one assumption in the model is the outer slope of the density profile, which turns out to matter. You get curves that look like this that sort of nicely reproduce the upper envelope of these points. And so what this means, if a point were above this curve, T cool over T free fall would be less than 10. You'd be accreting at an unsustainably high rate. The fact that most of the points fall below this point, these curves, is interesting. It means that feedback's a little bit less efficient than it needs to be. You're overheating the gas a little bit, and there's probably interesting astrophysics there. But it is consistent with the model.
What's the physics in the breaks on these curves? So maybe you mentioned it.
Oh, this is the break in the cooling curve where cooling by atomic line starts to become important. So this is the Bremsstrahlung part. Yeah, good question. That's at about a keV for a third solar. Okay. So that was the first project I wanted to describe. It's a theory for when cold gas forms in clusters and where. It turned out to have implications for feedback and for the density structure of the gas and galaxy clusters.
So I'm still a little confused at the beginning when you had that picture on the right where small clouds didn't form.
Yes.
And it's just I mean, the gas does cool there.
Yep.
It's just, I guess I'm missing what the two-line description is for why you don't get clouds.
So I think the physics is here, right? So if you
the saturation I see, yeah.
But that is
why it saturates at such a low level, basically. Why you don't get large delta rho over rhos.
Right. And so the saturation is everything, right? Delta rho over rho will grow exponentially. Nothing grows exponentially forever. It stops. And so where it stops is key. And so in this case...
But what is making it stop sooner?
Yeah, when you look for a steady state, you're driving it on the cooling time. It dissipates on a time scale, which depends on the wave period and the free fall time. And so that parameter, the wave period over the free fall time, that controls the dissipation.
Okay.
And how that is compared to cooling. It picks out the amplitude.
Thank you.
I don't know if that...
No, that helped. Thank you.
Every once in a while I have to work through the algebra again to remind myself. Okay, so that was the first project. The second one relates to convection and mixing in galaxy clusters. And so I'm going to take a little bit of a break from cold gas, and I'll come back to it at the end. But this is a theory just for the hot gas in galaxy clusters. And the properties of it that are important are, first of all, that it's hot. It's like 10 to 100 million degrees. And then the density characteristic in the centers of clusters is like less than a tenth of a particle per cc. And this combination of high temperature and, depending on your perspective, low density, that means that the mean free path is pretty long. It's like hundreds of parsecs in the center of a cluster. And it rises to, it can be hundreds of kiloparsecs in the outer parts of the cluster. And so a very long mean free path, first of all, it means that even modeling this as a gas is maybe a little bit dodgy. But if it is a gas, it's going to be very thermally conductive. Thermal conduction is diffusion of particles. If the mean free path is long, particles diffuse like crazy.
So you're just saturated in some sense because your gradients are not as steep as the mean free path. Or your gradients are, is that what you mean?
The mean free path is smaller than the size of the system, so by quite a bit. So it depends on the size of the features. But a wrinkle on this is that the gyro radius is tiny. It's like the size of Earth, which I think in astronomy units is a nanoparsec. And so what that means is particles cannot cross magnetic field lines. They gyrate furiously around the magnetic field and go for many, many gyro orbits in between scatterings. And so thermal conduction is efficient, it's fast, but only in the direction of the magnetic field. And the plasma is actually very thermally insulating across field lines. And that totally changes the physics of convection. And it's a case where the equations are a little bit nasty, but the simple picture is actually very easy. And you can see why just in this picture. I'm drawing a blob of gas in a galaxy cluster threaded by magnetic field lines, and I'm perturbing it by displacing it up by an amount delta z. And in astrophysics, gas is usually very electrically conductive. And so if I take a blob of gas and move it, the field lines follow it. So as I move this up, it drags magnetic field lines along with it. And then I have very rapid thermal conduction along field lines. So electrons are zipping along the magnetic field. They want to make the magnetic field isothermal. So if I move this gas up, that takes field lines with it. I have conduction along field lines. Effectively, this is conspiring to make displacements isothermal. I move this gas up at constant temperature. And so if the temperature in the background falls with height, when I move this up, it's warmer than the surroundings and it wants to float. And that's an instability. I move it up, it responds by getting a buoyant force in the same direction. This can drive vigorous convection. And I just want to say this is essentially the same. The equations look different, but the physics is very similar to normal short-shield convection. Typically, we talk about displacing gas adiabatically. You move a parcel of gas at constant entropy. And so for convection, it's the entropy gradient that determines convective stability. The physics is different here, but because I have conduction in magnetic fields, it conspires to make displacements isothermal. I get a very similar criterion. It just depends on the temperature gradient instead of entropy, which matters for galaxy clusters. The entropy increases with radius, like a power law in clusters. They're very, very stable according to the classical short-shield criterion. It's virtually impossible to mix gas radially in clusters. And this is seen in simulations. You cannot do it, no matter how high you turn up the AGN. The temperature profiles fall with radius in galaxy clusters. And so if you account for this plasma physics, they're actually convectively unstable. And I believe that there's observational evidence for it. The metallicity profiles in clusters, in a few cases, have been measured out to megaparsec distances, all the way out to the virial radius. And they find, amazingly, a third solar all the way out. The metallicity profile is almost perfectly flat. And this is something that cannot be reproduced in cosmological simulations. If it's convectively stable, you cannot mix radially, no matter how hard you try. You're just working against the physics. But if it's convectively unstable, this would just naturally come out of that. So I gave you kind of the cartoon picture of how this convection looks. to show how it looks in a numerical simulation. So this is still in the quasi-linear phase. I'm showing an unstable temperature gradient. It's hot on the bottom and cold on the top. Black lines trace the magnetic fields. And so whereas before I gave you a blob, here you have a simulation, but you can see basically the same thing. I have this kind of plume of rising buoyant gas. It takes the magnetic field with it. Thermal conduction is making the gas isothermal along field lines. It's the color along the field line. And so gas that goes up is warmer than the surroundings and floats. And similarly, I have these columns of cold sinking gas. They rake out magnetic field lines. And if you let it become nonlinear, it drives vigorous convection, just like short-chilled convection. It drives turbulence, radial mixing, and things like that.
So if you eventually get cold clumps that are magnetically draped and hence stay cold?
This is all, the temperatures may be changing by tens of percent or a factor of 3 or something. This isn't a factor of 100 or 1,000 like you have. So I'm really just focusing on the hot gas. So that's the physics of that convection. Something that came out of it, which was a little bit unexpected, is that the temperature profile really matters in clusters. The fact that the temperature profile falls with radius makes them convectively unstable. That's important, presumably, for the astrophysics and metal mixing. And there was no theory for that. People thought the entropy gradient mattered. There were theories explaining the entropy profile, but there was no theory for the temperature profile.
Can you just remind us why the cluster people are so obsessed with entropy? I know that that's a big... Is it because this entropy floor, or...
I have to look on Mars.
They're perverse.
Basically because of this theory.
Yeah.
So the idea behind
the
this...
Schwarzschild theory.
Yeah. So the fact that this rises with radius, the idea in the cluster community was that high entropy stuff floats to the outer radius, right? And you can make a theory that produces these entropy profiles. But I think that's not the correct story. So I think the temperature profile is actually something that's important.
Okay, that was my next question.
So I made the theory for the temperature profile. Yeah.
So when the instability sort of bends these magnetic field lines, what direction is magnetic tension wanting to pull it?
Good. So the sign of tension would be to suppress that, right? This is stretching out magnetic field lines that adds energy to the field. It's exactly the kind of thing that magnetic tension would suppress. Magnetic tension is scale dependent. It goes like the curvature of the field. It's most important on small scales. Convection is scale independent. Something floats depending on its density contrast, independent of how big or how small it is. And so if you put in numbers for the field strength, and the field strength is measured in clusters, it's sort of 1 to 10 microgauss, it can suppress this on kiloparsec, 10 kiloparsec scales, kind of like the resolution limit in the observations. But for a very strong field, you're right, it can suppress this. Okay, so a theory for the temperature profiles in clusters. Yeah, so this is just another observation. It's a little bit ratty, as X-ray data tends to be, but you can see the temperatures falling with radius in the outer parts of clusters. And it is a little bit surprising, and Ski's not here, but he asked about this in one of the Astro Lunches a couple weeks ago. If you take the conductivity of the plasma in the age of the universe and sort of normal assumptions about the mean free path, there's actually plenty of time for heat to diffuse across the cluster. And the naive prediction would be that the gas would be isothermal. And indeed, the first simulations that tried to study convection in clusters concluded that it wasn't important, because what happens first is conduction moves heat around and makes them isothermal. This is not what we observe. And I think that simulation is not right. And the key that it missed is that it has a boundary condition here.
This was rationale. He was including the suppression of conduction across magnetic field lines.
Yes. Yeah.
Even there, it goes isothermal.
Yeah, but you have field lines that connect disparate parts. Yeah, and so the key that's missing is that he has a boundary condition here. And a real galaxy cluster doesn't have a boundary. It's bounded by a virial shock that can respond dynamically to how heat moves in the cluster. And that turns out to make a huge difference. And so I made a simple analytic theory for the temperature profiles in clusters. I'm showing first a simplified case where I assumed the gravitational potential is isothermal. That allowed me to solve it analytically. And when you do hydrostatic equilibrium in an isothermal potential, the temperature at the center has to be the virial temperature. It's almost like a boundary condition in that case. The cluster is bounded by an accretion shock, And there are jump conditions at the shock that depend on the accretion rate, which is basically determined by cosmology. And so there's a shock out here with a temperature that's kind of determined by cosmological physics there. And then to get the intermediate temperature structure, you actually have to solve an ODE. You accrete shell by shell and track how the shock evolves as a function of time. But basically what you get for an isothermal potential is a straight line that connects these two temperatures. And the sign is that slowly accreting things, they have a weak shock, and the temperature is low compared to the virial temperature. And quickly accreting things, as you accrete faster and faster, the shock moves in, you shock to higher temperatures, and it approaches, or in crazy cases, even exceeds the virial temperature. And there's a special temperature where you get an exact isothermal profile. You can solve for it analytically. The d log mdt times the dynamical time. It's like the square root of 3 over 32, if I remember. You can do it for this case. The point is that galaxy clusters do not, in real life, accrete that fast. It's an accretion rate that's of order the mass doubling times, like the dynamical time. And in lambda CDM, things accrete more slowly. So they're sort of in between these two curves. And you have temperature profiles that change by a factor of few from the center to the virial shock. Yep.
So Mike, I would have naively thought that the speed of the accretion was just set by the depth of the gravitational potential. And what you're saying suggests it's much more complicated than that, and I'm trying to understand why.
There's another parameter that's where the shock is.
Mm-hmm.
So as the shock moves in, you accelerate more and more and more before you shock. If the shock moves all the way out to like the turnaround radius,
yeah.
that would be an extreme case.
Yeah.
It barely falls, right? And you don't thermalize any kinetic energy. And where the shock is an eigenvalue of the equation. It depends on the past structure of the...
This is like how much mass it's pushed out of the way or something.
Yeah.
What's your shock condition? What do you use to determine the shock?
Just the Rankine-Hugoniot jump conditions.
But you're attaching onto a settling solution inside with no cooling?
Okay, so numerically the way it works is I assume a shock condition, and then I accrete shell by shell, so I have entropy as a function of mass, okay, forgetting about convection for now. And then I solve hydrostatic equilibrium. So I assume a shock condition, and I integrate in. And if I reach mass equals 0 before R equals 0.
But no cooling?
No cooling.
For that calculation?
Right.
So the entropy is frozen post-shock for all the fluid?
Yes, exactly.
So I'm trying to relate to a problem I know, where like if you've got a stellar wind or a supernovae, you've got ejecta going outward. That shock forms when kind of like the mass of ejecta is similar to the mass that you've swept up. So like, is there some analogy here hydrodynamically for where the shock forms? It's like, this is the picture I have in my head that I'm trying to...
Yeah, I mean, in this case, there is an edge of the cluster, right? So gas is falling in, and eventually it's going to smack into the cluster in shock. And the ram pressure of the falling in stuff, which is set by the accretion rate and the depth of the potential and where the shock is. And then the pressure, which also depends on where the shock is. You want to balance between those. And that balance, I can't give a closed form solution for it, but it's an eigenvalue. So I assume a shock radius, and I integrate in, and it either works or it doesn't. And then I can assume a different shock radius, and I integrate in, and it works or it doesn't. There's a single solution, but I never found a closed form solution for exactly why it is where it is.
So in the adiabatic case, we just would have had, if we're at turnaround, and we want to get to virial equilibrium, the thing's going to have to collapse by at least a factor of 2. And like that's where you form the shock. So the difference here is just the history of the cooling during this process?
Yeah, it's not exactly a factor of 2. It could be a factor of 1.8, or it could be a factor of 2 point something. Right? The shock has a little bit of freedom. This isn't the dark matter, which is self-similar.
If you had a power law density perturbation, then it would be a fixed fraction of the turnaround radius.
Yeah.
But then this, if you have non-self-similar initial conditions, then it's just a function of the global initial density perturbation that produced the mass accretion.
Like the shape of it, because that's the distribution of it. Okay.
Yeah, the sign is that the shock moves in for higher accretion rates. And that flattens the temperature profile, which is kind of cool. The temperature profile then encodes information about the accretion rate, like you could, in principle, use to test lambda CDM. I'm not doing that, but it's possible. So that was for an isothermal potential, which I chose because I could do it quasi-analytically. If I do a more realistic potential, like an NFW, I get a shape that looks like this. It's actually similar, nicely similar to what we see in galaxy clusters. But the basic intuition is roughly the same.
And do simulations that, of course, are just capturing this physics, do they then just get these temperature profiles as well?
They do, yeah. There wasn't a theory for why. People focused on entropy because they thought it was.
But you're saying it's just variations in the cosmological accretion rate?
Yep. If it forms a little bit later, the accretion rate's higher, would be more isothermal.
So I think I caught up with you, and I can picture that temperature profile just as a history of the velocity of the accretion and where the shock was.
Yeah, exactly.
And then your argument is that this is then what gives rise to the convective instability.
Yes. It's the fact that the temperature falls with radius turns out to be interesting.
Mike, how much of the temperature, if I'm down at your temperature peak, let's say for the purple or the red, how much of that temperature is set by the later adiabatic compression post-shock?
Oh, it's basically entirely set by the gravitational potential.
So there's very little compression post-shock for the gas. Because I mean, you're saying you're not allowing the entropy of the fluid elements to change, so I agree the entropy is frozen by the shock.
Yep.
So now the only way you're going to change the temperature is to compress it. You're saying it doesn't. There's no density change of the fluid elements, so their temperature is frozen.
The temperature is different than it was when it accreted, I think.
Well, it's a question. I'm just trying to understand how much compression you get post-shock.
I mean, I haven't quantified it in those terms. When you solve for hydrostatic equilibrium, the peak temperature is of order the virial temperature, which that's the answer I was expecting.
Right? I mean,
Yeah.
It has to be variable.
I think if you had different entropy profiles, which is kind of what these different curves are, they're different accretion histories. Okay, in the case of an isothermal potential, the central temperature doesn't change at all. In this case, it changes like from 0.9 to like 1.1 or something like that. But these have very different entropy profiles. But this is more or less dictated by the gravitational potential. The gas, it doesn't have to be exactly the virial temperature, but hydrostatic equilibrium is going to make it close in the center. Okay. I'm going to speed through this, but I just want to show it off because it's cool. So if you want to simulate convection in a galaxy cluster, then you have to self-consistently find the virial shock because that's what's setting the temperature profile, which is what's driving physics. And so I invented a simulation technique that I'm calling a semi-cosmological simulation. It's still an idealized simulation that I can run at high resolution and isolate different fluid dynamics processes. But it has the cosmological physics, the evolving gravitational potential, and the accretion shock that's necessary to reproduce the temperature profiles. And so this is what the simulation looks like, including this type of convection. And so you see, I made it roughly spherically symmetric. It's 3D. So I have spherically symmetric accretion. Gas comes in from the turnaround radius, twice the virial radius, which is typically what separates the Hubble flow from stuff that's accreting under the cluster. I treat that as a boundary condition in the simulation. And you can calculate in lambda CDM where that is. Apply that as a boundary condition, put in a dark matter potential by hand that's calibrated from the NFW profile from dark matter simulations. Gas falls in, it self-consistently finds the virial shock, which is an eigenvalue of the structure. And it nicely reproduces this temperature profile that you see. Cold in the center reaches a temperature maximum, falls by a factor of roughly 2 to 3 by the virial shock. And in this case, I was using the simulation to study convection. And so you see hot plumes that are rising out. Just to show that they're actually hot, I'll again show the simulation, not with temperature, but temperature fluctuation. And you can see hot things going out and cold things going in. The point is that they move of order the virial radius over the Hubble time. They can mix galaxy clusters, and observationally they seem to be well mixed. But the thing I'm really excited about with this isn't so much convection. It's this, which looks like boring line plots, but I'll explain it. I'm showing temperature and entropy profiles for 3 different clusters. And this is one that accretes quickly, that forms late. This is a typical galaxy cluster, and this is one that accretes slowly that formed early. And the only thing I want to say, I should have put data on this plot. Okay. You'll have to believe me that
it's much cleaner this way, I'm sure.
The error bars are big on the data, but it does nicely reproduce the data. But the thing that I'm really excited about is the blue curves are this kind of almost analytic model that I get by solving an ODE. And the red curves are a fully nonlinear, fully three-dimensional hydrodynamic simulation that's run for Hubble time, right? And so the point is that I have a theoretical model, almost analytic, that's predicting the outcome of a simulation that's run for Hubble time. And so this is a very well-controlled numerical setup. I know exactly what it's going to do, and I can put in extra physics and test what it does. And so I use it to do convection. I'm working with a student at Berkeley who's adapted this, basically changed the cooling law to do galaxies, and he's put in a model for galactic winds. And he's studying how the stability of the virial shock depends on a function of mass, going back to some of the early models of galaxy formation, and doing things to try to predict column densities of different ions. Actually finds a relatively high column density of oxygen-6, which surprised us, which we're looking into. The point is that this is a very adaptable simulation technique. I think there's a lot more that you can use this for, and it's kind of intermediate between analytic work and the full-on cosmological simulations. Again, just showing off using it to do convection. One of the fun things that you can see is that the gas is only convectively unstable when the temperature falls with radius. Cluster temperature profiles are non-monotonic. They rise in the center. And indeed, you see that there is no convection in the center. You just have azimuthal, stably stratified motions that wind up the magnetic field lines into these loops.
So with the merits are super high resolution such that you can do MHD and resolve temperature gradients that are very small. Is that the, I guess I'm just trying to...
I would say the merits are this, that it's exactly controlled. If I turn off all the physics, I know precisely what it'll do. And so if you want to study what a certain kind of wind does, or if you want to study what cosmic ray pressure does, or if you want to study convection, this is, you can add one thing in at a time. You have a baseline theory that's very well calibrated, and you can really zero in and understand the bit of physics that you want to do. That's something that's hard to do in a cosmological simulation where there's so much going on. And a lot of what happens is really determined by turbulence driven by structure formation, which may not always be well captured in the code.
So the differences for the type 0
Yes.
were quite a bit larger than type 1 and type 2. And is that an inaccuracy of the analytic model or the numerical technique?
Yeah. This is
it's a
where...
log scale, so that's not trivial.
This is not log scale. This is linear scale. So it's off by tens of percent. And really, the reason it's off is that the virial shock is off a little bit. And the type 0, this is really extreme. This is accreting so quickly, kind of going back to Lars's question earlier, that doing a quasi-static model is questionable. It's evolving kind of on the dynamical time scale. And so it's actually kind of amazing that this theory works at all. These are both meant to kind of bracket the extremes, and they're pretty rare. But yeah, the models aren't exact, but for cosmological simulations, there's really nothing like this. Okay. Last few minutes, I want to talk about dynamics of multi-phase gas in galaxies. I think the most important motivation for this are galactic winds, which seem to be a very characteristic observation of galaxies. We see cold, dense gas flowing out of galaxies at high speed. And this is annoying for theorists because we don't know how to explain that. There's still really no theoretical explanation for it. And the reason for that is that if you have a cloud of cold gas and you want to accelerate it, there is no paddle or fan or anything like that in astrophysics. Your only option is to blow on it, probably, unless it's born going fast, which is another possibility. But if you try to blow on a cloud of cold gas, you can work out fairly easily the time scale it takes to accelerate it. You get it from momentum conservation, and it's the time it takes that gas to sweep up its own mass in the wind. And so that goes like the radius of the cloud divided by the velocity shear, basically. And then from momentum conservation, it goes like the density ratio of the gas. It takes a long time to accelerate dense stuff just because it has so much inertia. The problem is that this is kind of linear in the velocity shear, and velocity shear does nasty things to gas clouds. Okay, it can drive shear instabilities like the Kelvin-Helmholtz that strip gas off of the cloud and mix it. Acceleration scales that way. that drives the Rayleigh-Taylor instability that can, again, rip the cloud apart and mix it. And then also, you can just drive a shock through the cloud that puffs it up and heats it to the point that it's not a cloud anymore. All of these things, I think, coincidentally, scale roughly the same way. Again, like the velocity shear, but this time like the square root of the density ratio. And the point is that if you have a cloud, if it's denser than the surroundings, by definition, this ratio is greater than 1, and the destruction time is shorter than the acceleration time. And the conclusion is that you cannot accelerate cold gas, you only destroy it. There are many simulations of this. This is an example. This has been tested many times in 2D and 3D with different codes by different groups. Everything comes to the same conclusion. And I'm no different. So I jumped on the bandwagon and also did a cloud crushing simulation. And this is what my cloud looks like after 1 destruction time. It's well on its way to being destroyed. And then this is what it looks like after an acceleration time. The color's the density on a log scale. And so, again, you see, I have not accelerated the cloud. I've simply destroyed it. And hydrodynamics looks the same regardless of how you see it. The important thing is that the types of instabilities that typically rip the cloud apart and mix them are exactly the types of instabilities that can be suppressed by magnetic fields. And so one of the things I tried was running an MHD simulation. And you get a very different result. I think the interesting one to look at is this point. This is the acceleration time when the gas should be co-moving. And indeed, in my simulation, it is co-moving. So the cloud got ripped apart. It looks kind of funny. The shape has changed. But the point is that I still have high-density gas moving at high velocity. The magnetic fields have suppressed mixing between hot and cold gas long enough in order to achieve entrainment. And I think the reason that this hadn't been simulated yet is that MHD is actually very sensitive to the initial conditions for the field that you put in. And so one of the first simulations, can I pause it? One of the first simulations that put in magnetic fields, when you put in a field, you have to choose an initial condition for it. And they did something that was very basic. They just put in field loops like this. And you can probably guess what will happen, right? Magnetic fields act like rubber bands. They want to compress. There's no balanced force. And so what this does is it squishes the cloud along the axis of the field. Gas shoots out along that axis. And you end up with these sort of dissociated magnetic field loops. And so you have a scenario where the cloud's already being ripped apart by hydroinstabilities. You put in a magnetic configuration that's unstable, and it's even more unstable, right?
Did you run this control?
No. I ran the control. This is also called a magnetic pinch, and it's actually used in the fusion community to actually drive rapid compressions. That type of field loop. So the field configuration that I put in was a tangled thing. And basically what you want in a field are these sort of twisted loop structures. So that's a case where the twisting creates a stress that wants to compress it. But you have magnetic filaments inside that provide magnetic pressure. And so this is a quasi, I won't exactly call it stable because it moves around, but it's something that's not going to rip the cloud apart. Okay, and this is what made the difference.
So that's the last image you showed where the cloud sort of survived?
Yes.
That's the initial condition.
So this is without the wind. I'm just showing how the magnetic field.
Yeah, I got it. But
yeah, Penn called it a control, which I like.
The simulation that you showed was a tangled field?
Yeah. I put a tangled magnetic
field. That's a tangled field.
Yeah. Okay. Another thing that helps with entrainment, this is the effect of the magnetic field inside the cold gas. You also probably have a magnetic field in the wind. And if field lines are frozen into the flow in MHD, also what that means is that gas can't cross field lines. And so if I have a ball of gas moving through a magnetic field, it sweeps up magnetic field lines. They have some tension. They don't immediately wrap around the cloud. They have some tension that gives them a shape. Basically, they increase the area of the cloud, enhancing the drag force and enabling faster entrainment. So again, sort of what you want to explain galactic winds. So that's one key thing that I think was missing from a lot of the cloud crushing simulations, is magnetic fields. Another thing, a lot of the simulations, particularly early ones, left out cooling. And if you write out the timescales, the cooling time for the assumptions I make is usually the shortest timescale around. It's like the exact thing that you shouldn't ignore. And I suspect the reason that most studies ignored it which is the reason I ignored it in that first thing, is that if you include cooling, the cloud fragments, and it's impossible to resolve, and you look at it and you think it's a numeric instability. But I think this fragmentation is real, and my colloquium will be about that. These are just simulations of it. I think the key is that for sort of 100 parsec sized things that you might expect in a galactic wind in the initial condition, if you include cooling and you hit it with a wind, you immediately fragment into these little tiny pieces, again, vastly increasing the surface area, the volume of the gas, hence the drag force, probably giving you faster entrainment. And I'm going to talk a lot about that in the colloquium.
It includes conduction as well, right?
Mm-hmm.
You're also modeling cooling and conduction, right?
There's no conduction in this. This is just cooling. Okay, so I argued that magnetic fields and cooling are both important. I showed you simulations, each with one but not the other. And so obviously I should try to do both. That's painful because in order to get cooling, I need very, very high resolution. And I cheated by doing these simulations in 2D. In order to include magnetic fields, it really has to be 3D. A tangled field does not make a lot of sense in 2D. In fact, you can't do it. And so I'm just starting to do that now. These are 3D simulations of shattering. This is the hydro case where I just have cooling. I'm not quite resolving it, but the simulation cost 1 million CPU hours. Doubling it would cost 10, and it's hard to argue that that's worth the carbon emissions that would come out of it, at least in my mind. But you can kind of see that it's fragmenting into little bits. The point is that when I include a magnetic field, that again suppresses mixing between hot and cold gas. Even though I'm not really resolving it, it still vastly increases the longevity of these clouds and produces something that I think is along the lines of what you want in order to model observations. So it's not exactly a two-phase medium. I have hot gas and cold gas. I have green stuff at intermediate temperatures. That's a combination of cold gas that's being shocked up to high temperatures and a combination of mixed gas that's cooling. This is the type of simulation that I think you can start to compare to observations. And it's a field where there really hasn't been a theoretical prediction. The observations are way, way ahead of the simulations. Okay, I had a summary, which I'll just speed through because I'm over an hour. But I talked about 3 projects: thermal instability, explaining when cold gas forms in clusters and where. That turned out to have implications for feedback in the structure of clusters. I talked about convection, which I think is interesting. It's a fun plasma physics problem. Exciting thing that came out of it was a theory for the temperature profiles in clusters, which has turned out to be nice. And then the thing I'm really excited about going forward is the semi-cosmological simulation method. This is an opportunity to try out new physics and really, really study it before incorporating it into future cosmological simulations. And then I described entrainment, a puzzle we have in galactic winds. And 2 processes that I think we're missing from earlier simulations are magnetic fields and cooling coupled with high resolution, both of which qualitatively change the results. So, thanks.
So we grilled you during your talk. Are there any further questions?
I've kept you a little past
You
the
know,
hour.
in that last picture of the shattered cloud, if you showed a map of pressure, would it be roughly uniform or not? Is this
Ooh, that's a good question.
essentially or not?
There are shocks in this. In particular, there are bow shocks over this, but they're not huge, right? They're Mach number of 1.5 or 2. Mm-hmm. And so there won't be enormous pressure differences. The pressure's within a factor of 2 of equilibrium almost everywhere. And in fact, that's actually physically what drives the fragmentation. I'll describe that later. Yeah, Anoop and then Jeff.
Would you get a bow shock for each one of those little fragments, or would you just get one big one where the cloud used to be?
No, each one if it's moving supersonically relative to its ambient surroundings. So it's a little hard to model because you don't have a single velocity anymore. Right? A nice thing about these kind of pre-shattering simulations is that you do just have one lump of gas, and when you strip it off, it mixes and it's gone, right? And so there is a single bow shock. If you include cooling and get this fragmentation, all of a sudden it's a much more complicated system. And the gas is not supersonic everywhere. And so we're still trying to figure out how much cloudlets shield one another, whether they're streaming instabilities that collect them back together, that kind of thing. It becomes a much richer system. Yeah, Joe?
So if I understand you're invoking a tangled field as a way of suppressing the cloud crushing instability, because that's your sort of initial condition.
Yes.
And so people have invoked tangled fields before for in a different context to suppress conduction in clusters, for example. I'm just wondering, could you just say, like, how do you get a tangled field? Maybe it's more plausible in a galactic wind because it's coming from the disk of a galaxy or the ISM of a galaxy. But I'm just like, how tangled, and how do you actually set that initial condition? Is that a plausible initial condition or a tooth fairy initial condition?
I would argue that it's the only realistic initial condition. And I think the key isn't so much that it's a tangled and force-free field. I think the key is that it's a not unstable field, right? Something like this is very unrealistic because it's an unstable configuration. You'd actually have to work very, very hard to set that up. And they do in fusion experiments. They have to work really hard. So the tangled field, really, I think you could think of it as like a balance. The magnetic forces don't exactly cancel, but they're balanced by turbulence, right? It's a dynamic thing that's not in the process of ripping itself apart. It's not in the process of collapsing. It's just it's a dynamic, kinetic, steady state configuration. So if there's a field at all, I would say, generated by turbulence in some dynamic equilibrium, it would probably be something like this. And the key for suppressing the instabilities isn't so much that it's exactly this type of field. It's that you have field lines kind of going every which way, and they suppress all of the different kind of unstable wave vectors. It has to be scrambled, but not unstable.
And yet, I mean, if the ISM of the Milky Way is turbulent, I would have thought this is exactly what the magnetic field would kind of look like in the ISM, but I thought in the Milky Way there was a more ordered magnetic field. And I'm having trouble putting together the picture of the ISM is turbulent, so it should look like this, with the disk of the Milky Way has an ordered magnetic field, so it doesn't look like this.
Well, I mean, what does ordered mean? I mean, this has large-scale loops that go through it that twist around. But it's not a single monotonic field that's in the same direction everywhere. I think that's really what you need in order to suppress these instabilities. Also, yeah, it is, in the case where the field is strong, it should evolve towards a force-free configuration, which actually is very much like this, where you have these twisted loops. And that can be on any scale. And the ISM is bordering on that case, where I think the magnetic energy density is comparable to other things. In a cloud, they're typically modeled as turbulent, and the idea is that the kinetic energy dominates over things, in which case the field configuration would mostly be determined by the properties of turbulence.
How can I recruit you to attend the DISCS program, Mike?
As soon as I'm not writing talks.
He's not giving 2 talks in one day.
Sorry, I interrupted you. You were going to complete a thought there. Except I just deviated you from the thought. I'm sorry.
No, it wasn't much of a thought. I think in general, it's interesting. There aren't a lot of constraints on the 3-dimensional structure of magnetic fields, which, as a theorist, I would love. Right? I would love to know what the field is in the galaxy. Something that Peng and Suching and I are thinking about is magnetic buoyancy in the galactic halo as a way to affect apparently observed lack of pressure equilibrium between clouds out there. Again, galaxy halos, I think it's published now, they have a metallicity profile that's measured to be flat, sort of like clusters. The convection driven by thermal conduction that I talked about probably doesn't work in galaxies, but magnetic buoyancy could. I don't know. I think there's a lot of interesting work to do.
Okay, why don't we call it a day there? In part because
it's only half time.
I know. Call it. Yeah. In part because he's got to give another talk. In part because I have to attend another talk in 15 minutes.